In this video, we will look at spanning tree protocol and how it operates. In this topology, we have 4 switches in a ring connected with different port speeds, mostly gigabit and Ethernet between switch 2 and switch 4. So the problem or the challenge with layer 2 topology is that you cannot have loops. You basically don't want to have loops in your layer 2 topologies, and that is the main job of STP, spanning tree protocol. So with loops, you will end up having broadcast storms which will bring your network on its knees. The job of spanning tree protocol is to create a loop-free topology by ensuring some ports are in blocking mode or blocking state. This doesn't mean that the ports will be down, it just means that they're not forwarding frames. One way to think of it is if you have, for example, switches connected this way, and we will get to the bottom of it in the next few slides. The job of spanning tree protocol is to elect a root bridge. So for example, say this would be your root bridge here. And then you still have a loop in your topology. So the next job of spanning tree protocol is to find which port between all the switches can be put in blocking mode. So for example, let's say this port here would be put in blocking mode. So by doing this, you have broken the loop and you have a loop-free topology. And essentially, this is what spanning tree protocol job is to determine the root bridge and break the loop somewhere in your topology. So let's take a look at the next few slides and start building up this process. We will start by looking or talking about the bridge ID. So the bridge ID is an 8-byte value, and this value is unique. The bridge ID is made up a priority, it's a 2-byte, and by default it has the value of 32768 on Cisco switches. And then the MAC address. So the MAC address is what makes the bridge ID completely unique. So if you think about it, assume that all these switches, switch 1, 2, 3, have the same priority of 32768. The only criterion that will make a difference between these bridge IDs is the MAC address. And for the purpose of spanning tree, a lower MAC address or a lower bridge ID is best. So lower is better in this case. And this bridge ID will be one of the first steps to elect the root bridge. So this is a very important piece of information here. The next information we need to look at is port cost. So in spanning tree, ports have costs, and this cost reflects the speed of the ports. So in the election process we will look at afterwards in the next few slides, a faster port means a lower cost. So a faster port, like a 10 gigabit for example, you can see here has a cost of 2, is much better than a 1 gigabit which has a cost of 4. So if you start thinking a little bit or making the analogy with routing protocols like vector path routing protocols like RIP for example, if you want to get from switch 4 to switch 1, would you go via switch 3 or via switch 2? So here switch 4 have to make a decision on where is my cheaper cost, where is the lowest cost to get to switch 1. And you can see here, if you aggregate the speeds, you have a gigabit, so that's your cost of 4, and then you're also using gigabit between switch 3 and 1, so you have a cost of 8. Whereas if you go via switch 2, your cost will actually jump to 100. So it's much better to go this way via switch 3 to switch 1 than via switch 2. So we will talk about costs in the next few slides again. This is another criterion that will later be used when we come to electing or building our loop-free topology. You can see here you have two different kind of costs. Both are IEEE standards. There are the costs that were used all the way to 1998. So they go from 100 to 2 for 10 gigabit. But at the time, having 100 gigabit or even 1 terabit in data centers, for example, was really not an option. So we did not have any costs allocated to port speed for 100 gigabit, for example. But later on, as things developed, so starting from 2004, there was a need to have a little bit more granularity. So this is why you can see two types of costs. Usually on Cisco switches, I haven't seen the values going from 2 million to 20. Configuration wise, you can switch between these two values or these two methods of calculating your cost by using spanning tree path cost method, and either using the long to have the post 2004 values, or using short to stick, which is a default, to stick to 100 to 2 for 10 gigabit. So now that we have looked at the two main criterion to build a loop-free topology for spanning tree, let's start looking at this process. The first thing that needs to happen is a root switch election. Remember we spoke about the bridge IDs and that the lower bridge ID wins and the bridge IDs are unique. So you fire up all your switches which are forming a loop. Each of these switches will claim to be the root switch for this topology. So each of these switches will start sending BPDUs. These are bridge protocol data units. And in these BPDUs, you will have every switch will insert its bridge ID. So switch 1 will be sending the BPDUs claiming to be the best. Switch 2 will be doing the same. Switch 4 will be sending BPDUs claiming I'm the root switch, and so will switch 3. Out of all these 4 switches, one switch will have the lowest bridge ID. And remember, the bridge ID is made of a priority and a MAC address. The priority, if left to default, will be the same. So the tiebreaker will be the MAC address. So the lowest MAC address will win. If switch 1 sends a superior bridge ID, once received by switch 2 will acknowledge or will see that switch 1 has a better bridge ID. It will stop claiming to be the root ID and will forward the BPDUs received from the better switch. Switch 4 will then receive, for example, the BPDUs from switch 1 and sees that they are superior to its own bridge ID. It will also stop claiming to be the root switch and forward the BPDUs received by switch 1 and forwarded by switch 2. Switch 3 will then receive the BPDUs sent by switch 1, either this way or via switch 4. And again, it will evaluate its own bridge ID compared to what is receiving, and let's assume that it will see that switch 1 has the superior bridge ID. In this case, all switches will agree that switch 1 is the root bridge. Once the root bridge is established, we need to assign roles to each of the ports in this topology. So we have two types of ports. We have the root port and a designated port. A root port is essentially a port that is receiving frames from an upstream root bridge. So in this case, if you look at switch 2, this is your root bridge. Switch 2 will be receiving frames from switch 1 via gigabit 00. So this will be your root port. On the root bridge, both ports will be called designated ports, and both these ports will be forwarding frames. The port assignment process will carry on until the point where one of the ports would be put in blocking mode. So for the time being, let's make the assumption that this port here would be put in blocking mode. So this port will not be forwarding frames. Any of the ports would be forwarding frames. So this is in a very high level how spanning tree creates a loop-free topology. The first thing is to elect a root bridge, and the second thing is to start assigning roles to all the ports in your topology until you end up with one port that is in blocking mode. Your root ports are selected and your designated ports are selected. So let's take a look at this example topology and go over the information that we have looked at in the previous slides. So here obviously we have a loop topology. We have this switch 1, 2, and 3, and 4 in a ring topology. We have a loop, so spanning tree has to break this loop and establish a loop-free topology. Each bridge switch ID is assigned. So the priority, as you can see, is 32769, and then you have your MAC addresses. So to make things simple, I have assigned 111 for switch 1, 222 for switch 2, and so forth. So here, what is the first thing that needs to happen? Spanning tree has to establish a root bridge. So let's start our election. So each of the switches will claim to be the root bridge until it receives a superior bridge ID from a neighboring or remote switch. So in this case, since the priorities are all the same for the 4 switches, we have to look at the MAC address as the tiebreaker. The lowest MAC address is on switch 1, which makes switch 1 the root bridge. So the root bridge is now established. Remember, both ports, or all ports, will be designated port. I'll just change the color here. Designated port, and designated port, which means that this port here will be forwarding frames. Now let's take a look at costs. Remember from the previous slides that if you have a gigabit speed, the cost per port is 4. If you have 10 megabit or Ethernet, the cost is 100. So let's take a look at switch 2. What is the lowest cost to get to the root bridge? Will it be directly via switch 1 or via switch 4 and 3? Here you have a cost of 100. And then you have a cost of 4. And then a cost of 4 out of one of these 2 links. So either I reach the root bridge via this port with a cost of 4, or I have to go via switch 4, which will be 100 plus 4 from switch 4, and then plus another 4 out of switch 3, so 108. So the quickest way, or the lowest cost, is to go directly to switch 1. So this becomes my root port. Let's move on to switch 4. Same election process or same valuation takes place. Again, it is lowest cost to go via switch 3, so it makes gigabit 00 my root port. So let's start marking this port here. Now let's take a look at what happened between switch 2 and switch 4. Here spanning tree has to decide where to place or where to select the designated port. So there has to be an election that happens between switch 2 and switch 4. Comparing switch 2 and switch 4, switch 2 has the lowest MAC address, which means that switch 4 receives better or superior BPDU from switch 2. In this case, switch 2 will become, or Ethernet 01 will become the designated port. Ethernet 01 on switch 4 goes into blocking state. So you can see here in this segment here, assigning a role to a port is also depending on the criteria or on which switch has the superior BPDUs. So let's apply the same principle that we have used between switch 2 and switch 4 to switch 3 and switch 1. As you can see, we have sort of a loop between switch 1 and switch 3 in the sense that switch 1 and switch 3 are connected by 2 links, which forms a loop. So we can't have both gigabit 02 and 03 as root ports. Only one of them will be root ports. So there is another selection process that takes place here when the priority is the same and when the MAC address is the same. Since these 2 links end up on the same switch, switch 1, which has the same MAC address. So you can't use the MAC address here as a tiebreaker. So the tiebreaker becomes the port ID. And again, the lowest port ID on the remote switch is better. So from the perspective of switch 3, gigabit 02 should be the root port because gigabit 00 is lower than gigabit 01. So this gigabit 02 here becomes my root port. And to break the loop, gigabit 03 goes into blocking mode. So now if we look at our topology as a whole and review the spanning tree loop-free topology process, first, we've elected a root bridge. Second, we pulled our root ports. Then we assigned our designated ports, and then we started blocking ports. So what we end up with is actually a loop-free topology. So if you look at it here on the side, you will end up with switch 1 here, if on the top of the tree, and then you have your switch 2, then you have your switch 3, and then you have switch 4. So there is no loops at all. It's because between switch 2 and switch 3 we have a block on Ethernet 01. So once your spanning tree has settled and you have your root bridge selected and you have your ports assigned as they should be, blocked and blocked, your designated ports and so forth, the topology will actually settle. Every switch will be sending BPDU hellos, will be sent every 2 seconds. If anything happens in terms of outages or anything changes, so for example you have a breakage here, the whole process is repeated once again. So you have to go, all the switches have to go again through the same process of electing your root bridge and assigning roles to all the ports in this topology. So how long does it take for the whole topology to reconverge? For any switch to take action and actually acknowledge that there is a problem, you have to wait a max age. So the max age is 10 times the hello interval. So there's 20 seconds wait, which is quite long by today's standards. Then the ports will go into listening mode. For 15 seconds. And then they will go into learning mode for another 15 seconds. So we're looking at 50 seconds before a port starts forwarding, which is definitely way too long. So assume, for example, you have a PC connected to this switch. When you plug in your PC, or there is an outage on the port and the port comes back up again, you don't want to be waiting 50 seconds for this PC to get his IP address and be online. So one of the improvements is to use a feature called Portfast. And with this feature, essentially, the switch on this port will skip all of these steps. So what you're telling the switch is that I am not connecting switch 4 to another switch. Please don't go through all these steps, waiting for the max age and listening and learning and what have you. So just start forwarding packets in and out of this port. So at a very high level, this is essentially how spanning tree protocol works. And this is irrelevant of the standard, whether it's 802.1d or 802.1w, rapid spanning tree. It does not make any difference. The difference between standards are mostly improvements on the conversions times. So rapid spanning tree will obviously be a lot faster because of different mechanisms and different roles. So this is on a very high level how spanning tree operates or works to establish or create a loop-free topology. I hope you have found this video informative, and thank you for watching.